to be the closing talk for this semester. And today I'm going to talk about our recent work with my advisor, Professor Stanley Osher at UCLA and Wu Chen Li from University of South Carolina, another USC, about the work that we use the score-based neural ODE and normalizing flow to solve the mean field control problem. To start with—
I think you want to say mentor instead of advisor.
Yes, mentor, sorry. Yes, and to start with, I would like to mention a lot of AI product that you must have seen many of them, including the AlphaGo, Gemini, ChatGPT, and so on. These AI agents are changing the world, and it also has a great impact in academia. And actually, many of these AI problems can have a control model. And with the optimal control problem being the center, we have variant formulation of control problem, including mean field games, optimal transport Schrodinger bridge, flow matching score-based method, and so on. It has traditional applications such as economics, finance, interacting particle systems, and also filtering problems. And it also has many modern machine learning applications. Of course, these optimal transportation and Schrodinger bridge also has applications in machine learning. And applications include sampling, normalizing flow, diffusion model, energy-based model, and so on. And all of these can be formalized into the optimal control problem. And next, let me give a brief formulation for the control with the mean field element inside. So let me briefly introduce the formulation of mean field control problem. The goal of the mean field control problem is quite direct and simple. What we want to do is to minimize the cost functional denoted by J alpha, where alpha denotes our control. It is the expectation of the part of the sum of two parts, one running cost and one terminal cost. The running cost is integrated through a time horizon from 0 to capital T, and the terminal cost is evaluated at the terminal time capital T. And this is subject to a state dynamic xt, which satisfies a Makin-Vlasov type stochastic differential equation with drift b and diffusion sigma. Here, all the functions f, b, and sigma are functions of t time, xt, the state, mu t, the distribution of xt, and alpha t, the control process. And here we are minimizing this cost functional among all admissible control processes on the filtered probability space. And throughout this talk, we will consider the closed loop control, which means that the control process alpha t, although being stochastic, it has a deterministic function in time t and state x. And another remark for the difference between mean field game and mean field control, because I know that some of you may doing the mean field game problem in finance, and it is slightly different from mean field control in the sense that in mean field games, there is no central planner, and as a result, when you make a small impact on the control, it does not impact the whole population, and as a result, we seek for a Nash equilibrium. And well, in the mean field control problem, we have a central planner, so we want to minimize the population loss directly. And I have been working many years on the control problem, so I would like to introduce a control toolbox that I summarized. And there are many important topics that we can study for control problem, and it can be basically categorized into two classes. One for theoretical analysis and another for practical algorithms for computing the control problems. It can be either stochastic control or mean field control or games. Starting with the classic theoretical stuffs, we have the classical Pontryagin's maximum principle and the HJB equation for the value function, and also for the dynamic programming principle. And also, since we have a state process, which is a stochastic differential equation, we have the Fokker-Planck equation and the corresponding density function theorem to describe the state. And in addition, since the control problem is closely related to the reinforcement learning problem, because in the control problem, we usually want to minimize a cost, where in the reinforcement learning, we want to maximize a reward. In the control problem, it is usually continuous time and state. In the reinforcement learning problem, it is usually discrete time and state, but they still share a lot of similarities. And
what about the exploration in reinforcement learning?
Yes,
Is that handled by stochastic control?
well, there is a formulation firstly proposed by, I believe, by Professor Zhou from Columbia University that also incorporate the exploration in the control problem. In that one, but this is not the topic for today. It's just that for the running cost, we add an entropy regularization term, which means that we don't want this alpha to be deterministic in X, but instead we add some entropy terms so that we force it to be stochastic.
So it's not closed loop controlling in.
Well,
in
I
this
think it can still be understood as closed loop, but it is no longer a deterministic function in XT. But the easiest case you may think of is that it has a mean of this guy with some variance at each time t. And in this case, we can incorporate exploration of reinforcement learning inside the control problem. And actually, I am currently working on a project that considers this setting.
Okay.
And I'm doing convergence analysis for policy gradient problem. And I'm sorry that this is not the topic for today, but if you're interested, we can talk later. And let's continue. And in addition to these, there are also many other useful techniques from reinforcement learning can be used to solve or to analyze control problems, including the performance difference lemma, gradient dominance lemma, which is very commonly used in convergence analysis of reinforcement learning, and also for the policy gradient to improve the policy, and for the temporal difference learning or Q-learning to learn the value function of the optimal control problem, and also their combination, which is the actocratic method. They are very helpful tools to solve control problem numerically. And in addition, we also have the normalizing flow, Eulerian coordinate, and the push-forward map in Lagrange coordinate that can solve the control problem because we have the state dynamic here. In order to describe the state dynamic, we can use these two coordinates, and also we have score-based method. And this is the toolbox that I conclude throughout many years of my research. And for today's topic, we are talking about a combination of these two, normalizing flow in Eulerian coordinate and the score-based method. And what I'm going to do next is to give a brief summary of some important one important topic of for both normalizing flow and score-based method. And let me move on again. This is the classic neural ODE paper that was out 7 years ago, proposed by Ricky Chen and other scholars. And in their neural ODE paper, they view a deterministic ordinary differential equation system as a deep residual network. And with this point of view, they can compute the derivative of the objective with respect to either the parameter or the initial state using the adjoint method efficiently. And after discretization, the ordinary differential equation becomes a normalizing flow when we parameterize the evolution of a density. And so we're in this example, in that special application, we will the composition. We will push a composition of the composition of a sequence of push-forward maps as a normalizing flow. And this is usually from a complicated distribution to a relatively simple distribution. But recently, this idea has been generalized. And whenever you have transformed one distribution to another through a composition of push-forward maps, we just call it normalizing flow. And as there was one important question addressed by the authors, Ricky Chen and other authors, that is one of the bottlenecks for using this normalizing flow to compute the quantities of interest is the computation of the determinant or sometimes the inverse of the Jacobian, which has a cubic cost in either the dimension of the state, which is denoted by Z, or the number of hidden units. This is a brief recap of the neural ODE system. And this is another well-known work. Of course, this is not mine. And this is the score-based generative model proposed by the Song Yang's group at Stanford in 2020. And the reason I want to mention this work because this is where score function becomes increasingly useful recently. And firstly, the score function is defined as the gradient of log of the density function. And it is useful because if we look at here, in the score-based generative model, if we start with some data which comes from a potentially very complicated distribution, if we run a long-run dynamic for sufficiently long time, we will move it to a relatively simple distribution, which is usually a Gaussian. And throughout this process, if we record the score function for the whole long-run dynamic, not just record, if we learn the score function, which is gradient log of the density along this trajectory, either through score matching or denoising autoencoder or other method, we will be able to reverse this stochastic process and hence generate new data from this distribution, from the original distribution using the data generated from this easier distribution just by subtracting scalar function times the score function inside this dynamic. Okay, and
excuse me. So in this picture, what's known, what's unknown?
Here
P0
for this
is
initial
unknown.
distribution, we don't have the density function. We only have data. Okay, and if we run a long-run dynamic,
So that F and G is up to our choice? Or?
Yes, F and G are up to our choice. The easiest way is that you set G to be a constant and F to be negative X, I think.
Okay.
So in this case, the potential function will be a quadratic function, and the invariant distribution is just a Gaussian.
So PTX, it's in P capital TX, it's independent of P0? Or?
When capital T is sufficiently large, this distribution will be very close to the invariant distribution of the SDE.
I see.
And in this way, if we record the score function throughout this procedure, then in order to generate new figure, let's say here we have a bunch of figures of dogs. Okay, here, Gaussian. We can generate just sample from Gaussian and run the reverse SDEs using the score function. And as a result, we can get new figures of dogs.
Okay.
Yes.
And that PT little t is because P capital T is given.
P capital T, it's better to say P capital D is very close to Gaussian distribution, which is the invariant distribution of the long-run dynamic.
There's a finite time horizon.
Yes.
Version Schrodinger bridge, you can, this one has no control, you just follow the noise direction.
Right.
And but if you do control, then get the exact distribution, and then you can also go back.
Yes, and I mentioned this because I want to stress the importance of score function. And here, if we have since after the introduction of these score-based score-based generative model and the previous neural ODE, a very natural question arises. That is whether it is possible to generalize the idea of neural ODE in order to compute the score function efficiently so that we overcome the cubic cost. The answer, fortunately, is yes, through our score-based neural ODE and normalizing.
That one can be clicked off.
Where?
Computer.
On my computer, I don't.
Oh, yeah.
Oh, okay, I see.
Yeah.
It's not on the same place. I
Y-
clicked it, but it's still,
Oh, still there?
yes,
Okay, yeah.
it's still here. I'm not sure. Oh, here.
Yeah.
Okay.
I still have a question.
Sure.
So you want the P capital T to be close to the normal, yes?
Yes.
So
close
for
to
that,
the-
either you need a capital T to be large, or I imagine, or the G is large, something like
Right,
that.
yes, you're right.
But that, let's say capital T is large, but if capital T is large, and then when you come back, it's also large T, so that error will also be,
Right, so it's not easy, so it's not easy.
okay. So, but it can be proved rigorously, it converges.
I guess at least we have, their group, in someone else group, they have practical examples that can
Okay.
generate new figures from the old figures.
Okay.
For this one, I think there are sample complexity results. How many data versus how many times you need to run close to the equilibrium. If I remember correctly, it's polynomial something, I forgot.
But in terms of convergence, I mean,
Yeah,
does this indeed converge back to the P0?
yeah,
Right,
It
yeah,
is,
it is,
okay.
yeah.
okay. And let's finally come to the major topic of today. We will do some math first. And for the probability flow, we start with a flow of random variable in d-dimensional Euclidean space denoted by zt, where t is the time. And we assume that it is obtained from a push-forward map denoted by capital T, which is a function of both time t, and the second input is the initial random variable z0. Okay. And of course, if we want to write down the density function of this flow of random variable, it satisfies the well-known Mondrian-Ampere equation.
So that this ZT is not a standard process. It's the measurability is all on the Z0, yes.
Sorry.
So the ZT and the Z0 has the same randomness, yes.
Yeah, all source comes
Yes,
from
yes,
initial.
yes,
Okay.
yes. They have the same randomness, and of course, when t equals to 0 is identity map. Okay. And we will assume that this capital T is always an invertible map. And so it satisfies the Mondrian-Ampere equation that the density at time t times the determinant of the Jacobian of the push-forward map equals to the density at time 0. And if we take the time derivative of this push-forward map, we get a velocity field, and we denote it by f. And this we can, and then this. And we also assume that this capital T is sufficiently differentiable, sufficiently smooth. And in this case, this ZT can be viewed as an ODE dynamic that with drift F. Okay, and it becomes, and in terms of the density function, it satisfies the transport equation or continuity equation. That is partial T of rho plus the divergence of rho times F equals to 0, where F is the drift of this ODE or the driving force of this ODE. Okay. And actually, starting from here, we will be able to represent all the quantities of interest using an ODE dynamic, including the, the density itself, the score function, that is along the trajectory. Let me move on to the next page. Under this dynamic, if we denote the log of density by L and also the density evaluated at the trajectory by L tilde and also the score function, which is the gradient of the log of the density, again, along this trajectory by ST. And we also have a higher order Hessian matrix of the log of the density by capital H of T. Then we can derive all the ordinary differential equation system for all of these quantities of interest. Okay, and the derivation of these equations are quite direct, although not that not that clear at first glance, but you can trust that all these derivations are correct. We just need to take time derivative and then use the relationship of this guy and the continuity equation, and we can verify that it satisfies this ODE dynamic, The first one is just the state dynamic, partial T of Ct equals to F. And for the density and log of density, and we actually need a negative divergence of this F with respect to the state variable. And for the score function, it's a little bit more complicated. It's time derivative in T. Again, this is the score function along the state trajectory. It has two terms. The first term is negative, the Jacobian of F, which is a matrix. It transposes times ST. And the second term is the gradient of the divergence of F, which is a vector. So this equation is a vector valued ODE, similar to the first one. And the last equation is a matrix valued ODE, which is even more complicated, but you can trust me that it is correct. And you can see that in order to get the density, we need the first order derivative. In order to get a score, which involves the first order derivative of the log row, we need a second order derivative for F. And if we want to get the Hessian of log row, we will need third order derivative of F, etc.
So here F also is the mapping capital T.
F is the
given,
velocity field.
You know it or?
Yes, we need to know it. And in practice, either we know it ourselves or we parameterize it as a neural network, and then we can represent everything we want and then train the network through constructing some loss function.
You're going to use all the equations.
Actually, I'm going to use until here, and this guy is what we are developing. We have some preliminary results for some simple question. The most important one is this one. And of course, I want to clarify that we are not the first to put this equation online. And before us, the group from Peking University by Shen Zuowei, and also the group in NYU by Eric Madden, they have all they have also written this equation in their work, but to the best of our knowledge, we are the first to put it into practice.
And what will be the dimension of Z later on? Say let's say mean field control problem on R, one dimension of mean field control problem.
Yes, if it is one dimension, then Z is one dimension. And if we are in D dimension, then Z is D dimension. And this L is one dimension, S is D dimension, H is the Hessian, so it's D by D matrix.
So it's not an infinite dimension.
No, it's not infinite.
Mean field control, we say it's infinite dimension. Yes.
Sorry, for mean field control.
So here it's the dimension of the state process.
Yes, the dimension of state process is still D dimension.
Okay.
Okay. And actually, what we are going to do using this framework is to solve the mean field control problem, and we will parameterize this F as a neural network, and in this work, we will just use the basic multi-layer perception structure, but we are open to other structure. After discretization, with a naive forward Euler scheme, of course we can also try other scheme because it's just a discretization of this ODE system, and we get the discrete version of the ODE using the derivative of F. And if as the
derivative are all learned computed by backprop in the neural network?
When F is known, we can get the derivative directly. If F is a neural network, we can just use auto differentiation.
Yeah, that's a parameterized, right?
Yes, parameterized. And in another point of view, the first state dynamic can be viewed as
just one more question. So the previous comment when F you parameterize it, it's you get an approximation of F and take a derivative, or you parameterize the derivative?
We firstly parameterize it and then take derivative. And yes, this is this may cause some difficulty when we train the model, and but we manage.
Can you parameterize the gradient directly?
If we parameterize the gradient directly, yes, this is another way. But we also need the second order derivative, and also we need to ensure some consistency between the original network and the gradient network.
Right. It should be derivative. Yes. Okay.
And this is, of course, another way of parameterization. And in another point of view, in the normalizing flow, we view the map, push-forward map from Z0 to ZTN as a as the normalizing flow in the usual sense. And actually, for our log of density score function and even second order score function, we can also write down the corresponding composition of push-forward map, and we can view it as a score-based or the normalizing flow for a score function, which is just the composition of a bunch of push-forward maps. Okay. And we believe that this is a very efficient way here to compute the score function. And let me make some comparison with some basic
Excuse me, what's the theta? Theta are the parameters, the theta.
Theta include all the weight and the bias parameter in the neural network.
Okay.
And here I'm just considering a very standard form, but of course, the parameterization of F is flexible. You can choose whatever parameterization you like. And let me make a brief comparison of different way to compute the score function. And we will just compare the computational cost when we want to compute one trajectory of score function from time 0 to time t, in order to make it fair. If we use a push-forward map, then what we can do is that we firstly compute the logarithm of the Monge-Ampere equation and take a gradient on both sides. We will get that the score function equals to the Jacobian matrix of the push-forward map, negative inverse transpose multiplied by this vector. And we can see that it is unavoidable to compute the inverse of a Jacobian matrix, and which will, or at least you need to solve a linear system in order to get the score function. And the cost for solving a linear system is d cubic in general. And secondly, if we use the normalizing flow structure, then what we need to do, again, we firstly take the logarithm and then gradient of the Monge-Ampere equation, and then we can find that we still need to compute the inverse Jacobian of this normalizing flow, which is in general have a d cubic cost. And of course, this is just the most basic model. There are also other works that that develop special structure of the push-forward map so that computing this inverse is very cheap. This is another direction for reducing the cost. And of course, what I'm listing here is just the most basic model. And for our score-based normalizing flow, if we want to compute the score function, we only need to run an ODE dynamic where, for here, computing the Jacobian of a matrix, if we assume that the net width is of order d, where d is the spatial dimension, then computing the Jacobian matrix only costs d squared. And also computing the matrix vector multiplication also only costs d squared. So if we want to compute the whole trajectory of score function, the cost is d squared compared with the traditional d cubic cost. And of course, and another event, as I just mentioned, there are also other ways to reduce the cost, like designing special parameterization for push-forward map so that computing the inverse Jacobian is cheap. But here, we do not restrict the structure of F, and if for whatever structure, as long as the width is proportional to d, similar to the above, we will have a d squared cost.
So one dimension, how do you do? In one dimension, so the network width is constant order.
Yes, in one
No
dimension,
I mean in general.
this reduction of cost is not that meaningful.
Not that, so it's pretty much the same for
Yeah,
all of
right,
them.
right. In terms of computational cost, when the dimension is low, then it is not a big improvement.
Yeah, first, just to confirm, so far there's no mean field.
Right, the next page is mean field control.
And also, I thought I was following, but then I get lost on the big picture. What are we doing right now? Because it's a T of Z, T.
Yes, currently it is here I'm trying to convey you that this is a good way to compute score function. And we want to apply this formulation to mean field control problem. But we believe that there are broadened horizon. It's just in this work, we applied these formulation to the mean field control problem. Okay, and this is the mean field control problem we are considering next. And I'm writing it in the PDE formulation where we have a running cost, terminal cost, but this time instead of writing it in expectation, I write it as the integration with respect to the density function. And the density function we assume is the second order mean field control. So it is a Fokker-Planck equation instead of a transport equation. It also has the stochastic form.
What is L and F?
L and F are different running cost. One depend on the control velocity. The notation is slightly different from the previous page. And F is the deterministic function of the density rho.
So you assume they are separate.
Yes, we assume that they are separate. But if they are not separate, let me think. We can still do it, but for all the numerical example, they are separate.
So it indeed helps. It's easier for the numerical steps.
Yes, it makes it easier when we try to derive an HJB equation. Although I'll explain it later.
But for mean field gain, when it's separable, it's easy.
Yes.
So-called less Lyon's monotonicity.
Right. For mean field control, it's also easier.
Another comment is, so here it's local in the sense.
Right. It's local because if we want to apply this ODE system to compute the density, if it is not, it has some non-local interaction, then we cannot naively just compute the ODE this way.
Okay.
So in this work, we are just considering the local dependence for our mean field control problem. And since the dynamic is stochastic, we cannot directly make it an ODE system. Instead, we need to make a transform. It's called a blob trick, or someone call it Nielsen's transform in the Schrödinger bridge literature. That is using the fact that the score function equals to the gradient log rho equals to gradient rho divided by rho. We can put this diffusion term inside the advection part and rewrite the Fokker-Planck equation as a transport equation or continuity equation by defining a composed velocity f as the original velocity v minus this gamma diffusion constant times the score function. And with this trick.
Another question. Since it's local, I never worked on the local version. So is it clear the SDE will have a solution? Because supposedly, given a control, you have a SDE, yes?
Well, here.
So in your case, the forward one has no control.
We itself is the control function, and in this framework,
it does not depend on.
Right, it does not depend on the density curve.
Okay, I see. Okay.
But if it depends on the density, yes, the existence is not trivial.
Okay.
And after this transform, we can try to minimize the composed velocity f instead of minimizing the original velocity field v. The only thing we need to do is that here, original L is a function of v. We need to replace it by f plus gamma times the score function. And we are able to compute the score function efficiently. So there's no worry about this. And also, the constraint becomes a transport equation instead of a diffusive Fokker-Planck equation, or transformed from a stochastic differential equation to an ordinary differential equation.
So here you have defined f equal v minus that. So is this f plays the same role as the previous f?
Yes, this f plays the same role as the previous f. You can imagine that since we have already written the Fokker-Planck equation in this way, if we write down the corresponding dynamic, stochastic dynamic, there's no diffusion, there's no Brownian motion. Instead, everything is concluded in this composed velocity field f. And under this ODE dynamic. The particle-wise, they're different, but in distribution, they will be this. It will be the same as the diffusive Fokker-Planck equation. And what's next?
But then I have the comment because let me see. Previously, when you write a V, given V is a SDE is a standard. Now, if you view F as your control,
Right. No,
then the dynamic becomes F plus
sorry.
the gradient log rho. So rho get into the part of the coefficient.
Yes, the gradient log rho.
I mean, you think of the SDE.
Right. Yes, we can think of SD.
The SDE is a coefficient, the drift will depend on rho, no?
Right. Yes. Exactly.
Okay.
Yeah. So and so you can view this F. The original optimal solution, optimal velocity field V, subtracted by the score function. So yes, it depend on rho of to be more specific, it is subtracted by gamma times the score function. And after discretization of this ODE dynamic, we can get a discretized version of the loss function where the score function is replaced by ST, which can be computed through the ODE system. And also we can evaluate the other cost depending on the density and the terminal cost directly. And if we minimize this cost, in this work, we are using the atom scheme. And here, let me present some numerical results. The first result is a regularized Wasserstein proximal operator. And I know that Professor Chen has a lot of work on optimal transport and Wasserstein proximal. And here we are considering a regularized Wasserstein proximal operator. And it is well known that when we want to compute the Wasserstein distance between two distributions, we have the binomial Bernier formulation for where we only need to minimize the kinetic energy 1/2 V squared subject to the initial and terminal constraint of the two distributions. That's the optimal transport. And if we replace the terminal constraint by a terminal cost functional, then it becomes the Wasserstein proximal operator. And in this work, in addition, we add a regularization term gamma, and this is why it's called a regularized Wasserstein proximal. And this is just a optimal control problem. And at first, we take a Gaussian distribution where we have a true solution that we can compare with. And we can see that after training, our score-based model is able to correctly captures the density function and its evolution, which is plotted in the red and the blue line. The blue line is the true density, and the red line is the learned density using the ODE dynamic. And we can see that it learns the dynamic quite well. For this example, next we also try to change this terminal cost G function to be more complicated, which is a double well potential function given by.
I'm sorry. So this example, you know the true solution?
Yes, we know the true solution because it's just an LQ problem.
So this is on training data, right? So everything on the training data, you don't have a different
training data.
I mean,
when we draw the line, we sample new points. So I think it should be think of as a validation data.
Okay.
Yeah, at each step, we can resample. We resample points from the initial distribution, and then run the ODE dynamic to get all the quantities of interest, including the density. So this density is computed through the ODE dynamic. And in addition to a simple LQ problem, which has a clear structure, we also tried a double well, the same problem, but with a double well potential. And starting with a Gaussian distribution, we can see that it also accurately captures the evolution from a Gaussian to a bimodal distribution, which is actually come from a double well potential. And this is the terminal density compared with the histogram of the terminal particle distributions. And by the way, the terminal density, we don't have the exact formula, but using a kernel integration formulation, we will be able to write the true solution as a nested integration form. And we use a Riemann, just a Riemann sum to approximate that integration to get a reference solution.
Does this suffer from high dimension?
Yes, this is one dimensional example. So we are able to obtain a reference solution. In 2-dimension, we are also able, but in a high dimension, we are not able to get a reference solution. But we still put an example in the paper, not in this slides. And in that example, in 10-dimension, we try a double well example. We can observe that it successfully split point into 2 piles, but we don't have accuracy estimate because we don't have a reference solution.
So let's say 1-dimensional. So for this example, how much time it takes to do the calculation?
You mean the training, right? Or after training?
Okay, you for training.
Yeah.
During training, I don't remember
So
exactly.
it's what's the scale? It's in seconds or in hours or in days or?
No. Since it's only 1 dimension, it's very fast. I believe it's less than half an hour, maybe 10 minutes, 20 minutes.
Okay.
For this 1-dimensional example. But for higher dimension, we will need larger neural network and longer training time to make it more accurate. And this is the comparison of the true velocity field and the learned velocity field at time t equals to 0 and time t equals to capital T, which equals to 1. And this is the plot for the score function obtained using the ODE dynamic at a time capital T. And we can see that the ODE dynamic captures all of these quantities accurately. Let me see how much time do I have. Good. And another example I would like to share about is the flow matching problem. And at first glance, it may seem a little bit trivial. That is, the cost is just velocity field V minus the drift B of this without a terminal cost. And if we just look at this form, the solution will be quite trivial. The minimizer is unique, which is V equals to B. But the flow matching problem is still very meaningful. In some cases, the velocity field B is not known, and in this case, we cannot just directly get the true solution V. And also in our setting, in our formulation, if we make that transform, and instead of learning this V, which is trivial, if we learn the composed velocity field F, which equals to V minus gamma times the score function, this objective becomes not that trivial, and it is still meaningful in the sense that if we really learn this function F, it means that we can transform. We learn the Fokker-Planck equation in a deterministic manner. And in this way, if we get this true F, we are able to compute the reverse process of the ODE, which is quite useful in sampling problem. Okay, and the formulation is, again, we just replace this V by F plus gamma times the score function. And as a result, the cost functional becomes this guy, F minus B plus gamma times the score function. And the constraint also, again, goes from a Fokker-Planck equation to a transport equation.
So again, here you say B is unknown.
No, in this case, B is known. It's just that when others propose flow matching problem, it's very common to assume that B is unknown and B is obtained from maybe some filtering problem or observation. And this is a part that I'm not very expert at. And in our setting, what we want to do is to learn this composed deterministic velocity field that governs the dynamic. And as long as we have this F, we will be able to compute the inverse process of Fokker plot. That is, given a point sampled from terminal distribution, we can run this ODE inversely using this F and get the initial distribution. And this can be not done if we just run SDE. Okay, and again, for this, we tested on such a bimodal double Moon example where the drift is given by the negative gradient of a potential function V given in this form. And the invariant distribution of this above long-run dynamic will form a bimodal shape, which looks like a moon, which looks like two moons. And and we will start with a standard Gaussian distribution. And after training, we find that within some time, under the deterministic dynamic of using the drift F trained by the model, by through minimizing the flow matching loss, this guy, we can get that the particles are moving towards the two bimodal shapes, and also the second line gives the stochastic long-run dynamic, and we can see that our deterministic velocity field thus captures the behavior of a stochastic long-run dynamic, which means that although the first line, the state, the dynamic is deterministic, it shares the same improbability. It is the same with the stochastic long-run dynamic.
So in this example, what is B, the flow matching?
B is negative gradient V, where
that's
V is this
That's
potential
no
function.
drift.
Yeah. Yes. And if we make, and of course, this is a long-run dynamic, and the invariant distribution is just the e to the negative V divided by gamma. See, I think gamma equals to 1 in this example.
Just curious, because for this V, gradient of V is discontinuous, yes.
Gradient of V, really?
You have the absolute value of X.
Let me think. Maybe it's, let me see if it is a typo.
Because if you expand it, you will get a -6 absolute value of X.
Yeah.
So gradient is still fine, it's -1. So it's just at a 3, it's discontinuous. Probably it doesn't matter, just 1 point.
Yeah, good observation. I will check it later.
It's just at the 1 point, X equal to 3. So
Mhm.
probably it doesn't matter.
Oh, no, this is the X is in 2 dimension, so it is a circle. This I use this
Square root.
yeah, square root of x1 squared plus x2 squared. So
Smooth. Okay.
so yeah, so it's smooth.
Is it a differential or not? I get confused.
It is differential.
So
It is square root of x1 squared plus x2 squared minus 3. Then
Okay,
squared.
that should be fine, yeah.
So it
Should
is so it is smooth.
Okay, thank you. Yeah.
Okay. And
So this is not sampling, you're just trying to divert from one distribution to.
right. This is currently not sample. But if we want to sample this bimodal distribution, of course, you can start from here and run a deterministic dynamic, and you will get the same thing as long run dynamic. If you just want to sample from here to here, of course, you just need to run a long run dynamic. And we just want to show that here, using the deterministic dynamic, it can capture the behavior of a stochastic process.
So it's invertible, the flow, right?
Yes, the flow is invertible.
So by the way, it's still not differential at zero, not at 3. At 0, it's not differential.
Yes, if we take derivative, it becomes negative 1/2.
I know, I think it's not.
It's a barrier at 0, right? So the potential, so
Yeah,
you basically separate across the 2 parts of the zeros, right?
One-dimensional then, yes, but
Yeah.
2-dimensional it's.
This is a two-dimensional example, so.
But anyway,
But it's a very good observation. I will think about it to make it more rigorous. Yes, and the last thing I would like to present, if time is permitted, is called the HJB regularization, which looks quite complicated, but don't be afraid. It's just that we can try to derive the corresponding HJB equation for this for our formula for the modified mean-field control problem, where we subtract the score function in the control. And we can get that the solution to the mean-field control problem can be actually written in this form, where H is the Hamiltonian. It seems that I did not give the definition for Hamiltonian. Let us just see an easier example. In the Wasserstein regularized Wasserstein proximal operator, that first numerical example, we can show that the optimal velocity field F actually is the gradient of some function psi, and the rho and psi together satisfies the coupled Fokker-Plonk HJB system. This is not the traditional Fokker-Plonk HJB, but we can show that it is equivalent to the traditional Fokker-Plonk HJB. And we can see that for the Fokker-Plonk, there's no diffusion because it becomes a transport equation with the velocity field being gradient psi. And for the equation of psi, this is our HJB equation. The second order derivative of log rho and also the score function is involved. And actually, we can use this equation as a regularizer to further improve the accuracy. And since this equation holds, it should hold along the state trajectory ZT. And also, in this case, the Laplacian of the log of the density becomes the trace of Hessian of the log density. And the Hessian of log of density was denoted by capital H of t, which satisfies an ODE dynamic. Also, the score function satisfies the ODE dynamic, and we use ST to denote it. And using this formulation, we can actually add another term in the loss function in addition to the variational objective.
so this system becomes coupled forward and backward.
Yes, coupled forward backward system with the initial density and the terminal condition for terminal condition for the HJB equation. And you can see that here. It is subtracted by gamma times log rho. So if you take gradient, psi is actually for the traditional HJB equation, the terminal condition is just this guy. It's just this guy. We're related to terminal cost. But in this work, since we subtract a gamma times score function in the control, we also subtract a gamma times log rho in the HJB equation, so that gradient of psi is exactly the optimal velocity field. It's just a small trick. Maybe it's a little bit confusing when I present it here, but if you really read our work, it will be just a trivial shift compared with the traditional HJB equation.
How do we enforce this Hamilton Jacobi part into the primal flow?
We will just enforce it in the naive way that we penalize the residual of
Square.
Yes, squared. Wait, square or I can't remember whether it's squared or absolute one.
Is that good?
It improves accuracy in under some certain circumstances. And firstly, And by certain circumstances, I mean that for the LQ case where we parameterize it as a quadratic function. And we can, this is the example of the
So phi is the potential, right? Yeah, or not?
phi is the solution to the HJB equation. And this time, instead of parameterizing the velocity field F as a neural network, we instead parameterize this psi as a neural network and obtain F by taking another auto differentiation. So you can see that if we want to implement this HJB regularizer, we need one more derivative. And also, computing the HT needs third order derivative for F, which actually requires fourth order derivative of this psi. So we need one more order of derivative, and actually it complicates the training system. So we are considering an easier, simpler case where for which is the linear quadratic.
Excuse me, can you go back? So maybe can you go back? So maybe I'm thinking too much from the theoretical side. Do you have well-postness for this system in general?
The well-postness of this system is equivalent to the well-postness
Because it is the previous one,
of the original, of the traditional or the classic Fokker-Planck HJB system, because this is just a shift.
Right. But then if numerically you start to do this one, then introduce the errors, it is such a, because this one itself, if you just study this system, it's very hard to prove the well-postness, yes.
Right.
But then the numerical methods, maybe you cannot do the shift again, yes.
Sorry, what do you mean by do the shift again?
Because this one you say it's well-postness, it's because of the transformation from the previous one.
Right.
But then if you start to solve this system numerically,
Yes.
and then the well-postness will become an issue, yes.
You mean numerically?
Convergence.
Numerically, it becomes an issue.
The convergence, yes.
Right. This is a very.
Because if this system, you can easily prove the well-postness by contraction mapping, for example. Then the numerical algorithms typically will follow similar estimates and you can prove the convergence.
Right.
But these ones, the contraction mapping is such, it's very hard in general.
I agree, yes.
But anyway, I'm too much in the theoretical side.
Right. And actually, if we parameterize the in a very general manner, it indeed is super hard to train. So what we are considering is a simple case where we parameterize, where we know that the solution is a quadratic function in X, and we parameterize the coefficient as a network. And in this case, and also for the time derivative in T, we are using a finite difference scheme to a central difference scheme to approximate it in this form. And under such a special parameterization, so I'm sorry, it is restrictive. We will find that adding this HJB regularization indeed improves the accuracy, roughly from 10 to the negative 2 to 10 to the negative 3. But yes, I have to admit that it is restrictive. It is not very generalizable. And next,
A and B.
A and B is the parameter here, A and B. And we only want gradient psi, so C doesn't matter. The C doesn't matter. And this is another example for the flow matching problem, when we can see that for an OU process, we can see that again, adding H3B regularization will reduce the cost. And this is an OU process in 2 dimensions. And again, I would like to stress that if we use the deterministic probability flow, the behavior of the particles becomes quite interpretable and structured, in the sense that this is an OU process, which is a special Gaussian process. If we start with some Gaussian distribution, and here I only pull out the point that is within the circle with radius being the standard deviation. And along the trajectory, we can see that the points are always within the radius, within the circle, with the center being the mean and radius being the standard deviation. And if we run a long run dynamic, we can see that starting some points may go outside, and if we have some points that initialize the outside the circle, it may go inside. So using the deterministic dynamic, we have more structured behavior of the particle while preserving the probability distribution. Okay, and that's all for today, and thank you for listening.
Do you have any discretization error quantification for the step size?
Discretization error.
So for linear flow, you have a delta t, right?
Yes, we have a delta t.
So how that depends on this?
How this depend on the error?
You have continuous time formulation, right?
Yes.
And then
Of course, it depends on the numerical scheme, and we observe that. I also, in addition to naive forward Euler scheme, I also tried other higher order scheme, and actually, it does not improve accuracy because we have a neural network. So you can imagine that even if we have a higher order numerical scheme, the bottleneck of the error come from the parameterization of the neural network. So
the depth probably. FXT is a residual network or something.
yes.
So,
Wait, F itself is not necessarily a residual network, although we view it as a normalizing flow, as a
It's not,
discretization of neural ODE. But when we really do the parameterization, it doesn't matter what F we parameterize, because
What does residual network mean?
residual is basically a discrete version of ODE. ODE, you have DF or DT. That gradient is a finite difference.
Residual
and you
means there is an
parameterize
identity
instead of
map.
F, you parameterize by the derivative. And then you add them together, so you skip.
yes, residual means you have an identity added to it. No matter what F we have, it's a discretization of process. So we always has this identity map as a composition. Because here, this view it as a whole function, this part is identity. So for the parameterization of F is quite flexible.
I have another very naive question. Can you go back to the very beginning when you start introduce the score-based
Sure.
ODEs?
This is
this-
Song Yang's group in Stanford.
Yeah, so two questions. One is you have the data in the very beginning.
Yes, at the very beginning, we only have data. We don't have the
Right.
distribution.
So that in this procedure, what role does the data plays? When you go with the reverse.
What role
SE?
does the data?
So the data will play some role here, yes, in your algorithm, yes.
Yes, you can assume that you have a lot of pictures of dogs. So what you want is the distribution of all the pictures of dogs.
Yeah, but in this algorithm, when you do the score-based one, when you do backwardly, how the data come to play?
How the what?
The data
Data here.
of X0.
Well, this data help us learn the score function, which is the gradient log rule. And we are able to reverse this SDE only when we know the score function.
Okay. The second question is, since you have the data, you can just use the histogram to estimate the P0, yes?
Yes, this is another way.
Any comment why we go this, because that's the
I
straightforward.
believe that those engineering guys have a better interpretation. I believe that when X lies in a very high dimension, like figures or even videos, maybe getting a histogram is not a very efficient way.
Okay.
That's just my guess. I'm not an expert here for those engineering problems.
But I imagine if it's one dimensional, you given the data, then you just.
Yes, in one dimension, it should be.
Dimension is easy.
So you don't need this supposedly. One dimensional, can you just use the data and use a histogram and say that's P0?
The data?
Yeah, because you have data of X0.
It's smoothing the kind of density.
What happens?
Roughly.
Yeah.
In one dimension, because
It's well known that this has curse of dimensionality if you do
Okay.
this.
Okay, it's
That'll work
mainly
in
for the
high
high
dimension.
dimension.
It's mainly for high dimension. So have you compared with the other methods you mentioned, for, I don't know, the
for mean field control problem, firstly, if we want to numerically, we did not, because firstly, hope we compare it with other methods to compute the score function or solve the midfield control, because I think there's no other work that combine these two things together.
You mean normalizing flow and score?
Score and midfield control.
Oh, score and midfield control.
Yes, of course, there are a lot of score and solving the score function using maybe denoising.
But you can compare with other methods to talk about computing the estimate the value of the midfield control problem.
Yes,
or,
yes.
or optimal control, yes.
Yes, this could be done, and maybe the most naive one is just that.
But the main literature of the midfield control problem is a global one, I think, not the local one. Then
Right.
depend on role.
Well, what is global means here?
So
Here f is just a deterministic function of rho, but in general, it could be a determinist. It could be a function of the distribution.
Yeah, so my interpretation is here f depend on rho tx.
Yes.
The density
So that's
after
a
x.
local one.
Rho,
That's
the
this is the
global one. That's global one because mu t is the whole distribution. But if we replace this mu t by rho evaluated txt, then it's local.
So global means depend on the whole distribution or whole density, whole function rho t.
I see. So rho xt is just the states and the time, right? So
Right.
the single point
It's
is
the
a single
density
point.
at that point.
yes.
So
the whole
that
density
will make it easier. If we have the global distribution, when we have the HAB equation, it will have a term like functional derivative of the Hamiltonian with respect to the distribution as a density function. And in this case, the HAB equation will be much more
Does
complicated.
that mean no interaction or something?
Ah.
Still have interaction? If you have rho local, I mean rho xt.
We have
Not this one, the other one.
Still, there is interaction, yes, because rho tx depend on the neighbor, yes.
Yes.
So it's kind of a
Local interaction.
local interaction, interaction, yes.
And sorry to keep you guys that long.
Any more question? If not, let's thank the speaker again.
Thank you. Right. I learned that.